All right, today we're going on an expedition. We're going to be mapping these incredible territories that don't exist in our physical world but are hidden deep inside complex data. Get ready to see the invisible. So let's just jump right into the big problem. I mean, think about it. How do you visualize data that has, say, 100 different dimensions? Imagine a spreadsheet with 100 columns for every single row. How on earth do you look at that and see any kind of pattern? You can't just throw it on a bar chart, right? And the reason this is so tough is that we're fundamentally limited. We live in and perceive a 3D world, but our screens, our paper, everything we use to visualize information is flat. It's 2D. And that creates this huge gap between the data we actually have and our ability to really intuitively get a handle on it. So that's our first big challenge, seeing the invisible. When you think about the most valuable data out there today, from customer behavior to medical research, it's not just that there's a lot of it, it's that the data is incredibly wide. It has dozens, sometimes hundreds of dimensions. So the real question is this: how do you take all of that high-dimensional data and flatten it down into just 2 dimensions for our screens? But, and this is the key, do it in a smart way. You can't just throw away all the good stuff. You have to somehow preserve the hidden structure, all the natural groups and relationships that are buried in there. So how do we do that? Well, you need a special kind of tool. Think of it like a mapmaker's compass, but for this invisible world of data. And that tool, it's called t-SNE. Okay, yes, that is a mouthful, T-distributed stochastic neighbor embedding. But honestly, don't let the name scare you off. The stochastic part just means it uses a bit of randomness to find the best map. The core idea, though, is actually really simple and incredibly powerful. It's all about making the unseeable seeable. Now, this right here is the heart of how t-SNE thinks. It's all about one thing: preserving neighborhoods. So think of it this way. If 2 data points were close buddies back in their original 100-dimensional world, t-SNE is going to try its absolute best to keep them together on our 2D map. But if 2 groups of buddies are on opposite sides of the dataverse, t-SNE doesn't really care about showing the exact distance between them. It prioritizes keeping local friends together over the global, large-scale distances. And because it's so good at keeping neighbors together, t-SNE becomes this incredible tool for just exploring your data visually. You can spot natural clusters of similar things, you can see where different groups might overlap, and best of all, you can uncover these hidden structures that you would never have found just by staring at a spreadsheet. Okay, so this all sounds great in theory, right? But to really get a feel for how powerful this is, let's look at a classic, real-world example that shows it off perfectly: the iris dataset. So for every single flower in this dataset, we have 4 different measurements, things like petal length and sepal width. That means this data lives in a 4-dimensional space. It's a world we literally cannot see, which makes it a perfect job for our new tool. Now, this is the really cool part. We're going to give t-SNE only those 4 measurements. We don't tell it anything else. It has no idea, 0 clue, that there are actually 3 different species of iris flowers in this data. It's working completely on its own, just looking for patterns in the numbers. And here's the magic. After t-SNE does its thing and makes its 2D map, then we go in and we color the dots based on which species they really are. And what do you see? It worked. The algorithm, with no help at all, found the natural groupings and separated the different species into their own little clusters. That's incredible. But look closer, because it tells us something even more interesting. You see how one cluster is way off on its own, but the other 2 are kind of snuggled up close to each other, even overlapping a bit? That's a real insight. It tells us that these 2 species are naturally very similar in their measurements, and it explains why other algorithms sometimes get confused and think there are only 2 groups instead of 3. That structure was always there in the data, t-SNE just made it visible. Okay, so we have this amazing map, but just like any specialized map, you need to know how to read it, right? There are some important rules of the road here if you want to get real insights and not get misled. All right, this is super important, so listen up. Rule number 1, the axes, the X and Y, they mean absolutely nothing. Ignore them. Rule 2, the overall rotation of the plot is totally random. What matters is how the clusters are positioned relative to each other. And maybe the biggest rule of all, don't pay too much attention to the size of a cluster or the exact amount of white space between them. The only thing that truly matters is who is next to whom.
Here's another practical little quirk, especially if you're going to code this yourself. Unlike a lot of other machine learning models, you can't just train t-SNE on some data and then transform new data later. It doesn't work that way. You have to run the whole process, what's called a fit transform, on your entire data set every single time. You can't add new points to an old map.
And one more quick tip, you'll see a setting called the learning rate. The best way to think about it is it's like how patiently the algorithm arranges the points on the map. If you set it too low, like you see on the left, you just get a big, useless hairball. But if you keep it in that sweet spot, usually between 50 and 200, that's when you start to see those beautiful, clear clusters emerge. Okay, so let's pull all this back and think about the big picture. What is t-SNE really for? Where does it fit in your data science toolbox? Well, that brings us to the final and maybe most important idea. t-SNE is a tool for thinking. Think of this as your quick start guide. So when should you reach for t-SNE? Definitely for that first look at your data, when you're just exploring, trying to get a gut feeling for what's going on, before you start building heavy-duty models. But what should you not use it for? Don't use it if you need to measure the exact distance between clusters, and don't use it to actually build a predictive model. It's just not what it's for. And that really is the main takeaway here, the one thing to remember. t-SNE isn't a modeling tool, it's a thinking tool. Its whole job is to take something impossibly complex and turn it into a simple picture that sparks your curiosity and helps you ask smarter questions. So the next time you're faced with an invisible landscape of data, what new questions will you be able to ask?